So page 20, we already did most of this page except the middle part. This was the part where I said we're going to do the zero acceleration picture. But we're supposed to do 3 different situations with a skydiver: negative acceleration, zero acceleration, and positive acceleration. So here's the skydiver and they're going to have negative acceleration. So this is the negative acceleration one. Actually, I'll do it like this. So there's a skydiver, there's a skydiver, there's a skydiver. This is going to have negative acceleration, zero acceleration, positive acceleration. I'm going to draw all the forces acting on the skydiver. And if I want the acceleration to be negative, then that tells you something about how big the forces should be. So I'll take these same forces and put them over here, and which one should be the same? Drag or weight? You jump out of an airplane. What stays the same the whole time, your drag or your weight? Your weight. And it stays about the same. If you want to be a smarty pants, you could say that your weight changes. How does your weight change as you fall?
It increases as you get closer to you.
Yeah, technically you get closer to the gravitational pull, so your weight's going to increase, but it's going to pretty much stay the same. So weight stays the same, and we want net force. Let's see. We want acceleration to be downward, so net force needs to be downward. So drag needs to be what? Bigger or smaller than weight? Smaller. So this would be like right after you step out of a plane. The air starts to push you up. Your weight starts to pull you down. The weight's stronger than drag, so you've got a net downward force, which means you start accelerating. You go faster and faster and faster. As you go faster, what happens to these 2 forces? Which one of them starts to change? Drag. Does it get stronger or weaker as you fall? Stronger. So this arrow gets bigger and bigger and bigger, and it stops getting bigger when what happens? When it gets this big. So as soon as these 2 things are equal, then your net force is 0, so your acceleration is 0. So you stop going faster, and the going faster is what made the drag change. So you never change your velocity after that, and your drag doesn't change. But you can make a choice, and you can cause your velocity to change, and that's what's going to happen here. So in this one, we're going to have positive acceleration, and this is the skydiver. I've drawn them upright for a reason. Which of the 2 forces is going to be the same in this? Weight. Unless they got really scared and they peed their pants and it dripped out into space. Then they would weigh a little bit less. Or maybe they ate some bugs on the way down. Then they would weigh a little bit more. So if we're going to have net force that's positive and acceleration that's positive, then the drag needs to be what? Really big. It needs to be bigger than weight. So there's drag. So what could it be that could make the drag really big? Parachute. So there. All right. Those are kind of the basic drawings. Now we're going to do a really complicated version of this, where somebody jumps off of a cliff. It says helicopter, but I'm going to change it to a cliff. So flip to the next page. The table below describes the experience of a skydiver who steps off a cliff. You can make it. You can leave it as a helicopter, but cliff. I'm doing that because it's easier to draw. And off of the cliff. So they step off the cliff, then they're going to reach terminal velocity of negative 40 meters per second. Then they're going to pull the parachute cord. Has anybody ever been skydiving? Anybody want to? Yeah, not me. I don't want to. I like to do a lot of thrilling things, but not skydive. So if I were going to skydive, though, I would do this. I would jump out of the plane, and then I would fall, and I would just enjoy it. You know how they do little tricks. They tumble around, they tuck, they form rings, and then after a while, they pull the cord. So they get to terminal velocity first, then they pull the cord, and then they actually get to a new terminal velocity, and then they just sort of float down, relaxed at a slow speed, and then they touch the ground, and then they come to rest. And we're going to be showing the accelerations for all that. This says, for each step in the sequence, sketch a diagram showing the individual forces and the net force acting on the skydiver. So in last class, I did my pictures up here, but I think I'm going to put them down here because I ended up with stuff like on top of other stuff. So this, in the very beginning, this is the cliff, and here's the skydiver who has stepped off of the cliff. They're wearing their little backpack. Oh man, I'm going to redraw my skydiver. By the way, if you ever get a test back and you did well and I put a little smiley face on it and your smiley face is crossed out, sorry about that. Sometimes I draw a smiley face that's just not, it's just too weird looking, and then I euthanize it. And then I draw a new one. And I catch myself, I think, you know, all smiley faces deserve to live, but some of them just look wrong, and so I get rid of them. So I did that to the skydiver too. So here's the skydiver. Right here, what forces are acting on the skydiver? Tell me a force. Weight. How about drag? No. So just weight. So at the very beginning, you only have weight. There's no drag. Why is there no drag? You're not falling. There's no air rushing past you yet. So it's just that. And I'm going to write, I'm going to put in a little net force also, and that net force is equal to the weight. So what's the acceleration of this person? Negative 9.8. So little dot there, and I'm going to number this. This is number 1, like matching up here. And this is also number 1. You're going to do this kind of thing when you make graphs for the rockets. Okay, number 2 says the skydiver reaches the terminal velocity of negative 40 meters per second. So here's the skydiver in number 2. Oops, I got him turned around. So they're falling like this. There's the parachute still. And this is number 2. That's at terminal velocity, so what do the forces look like? What's the net force? Net force is 0. So that means I need 2 forces. I need drag, and what else?
Drag, the weight itself.
Weight, and they should be the same. So there's drag and there's weight. Okay. And what would the acceleration be? 0. So I'll just put it up here somewhere. So this is number 2. And in between here, negative 9.8, that's free fall. That's what you're doing when you first step out. And then you get to terminal velocity where the net force is 0, 0 acceleration. How do you think these are connected? Do you think it's linear? Do you think it's sort of, I don't know, would this be concave, convex? What do you think? Do you think you change your acceleration more rapidly in the beginning or close to terminal velocity? So think about this. As you get, let's see, let me go back to this picture. Basically you're going from this to this. As the drag gets really close to weight, then this net force gets really small. If the net force is really small, then this acceleration is going to be really small. And if your acceleration is really small, how quickly is your velocity changing? Not that fast. So it's sort of this self-diminishing. It's like a negative feedback loop where the more the more your drag changes, the less it changes. So the closer you get to drag and weight being the same, the closer you get to terminal velocity, the smaller your acceleration is that's driving you toward terminal velocity. So you actually never get there. You just asymptotically approach it. So it's more like this. Something like that. And in reality, in theory, you can't ever get there. Because as you get super duper duper close to it, you're going to have a super duper small acceleration driving you closer. And the closer you get, that your acceleration gets even smaller. So anyway, it's like this. But I don't really care. I'm not going to test you over that. So there's number 2. Skydiver reaches terminal velocity. And then between 2 and 3, the skydiver just enjoys life for a little while. So before pulling the chute cord, let's say the chute cord is pulled right here. What's going to happen to acceleration? Yeah, it stays 0. They just stay at terminal velocity until they change something. In fact, the thing that they're going to change is their cross-sectional area and drag coefficient. So right here, this is going to be the next thing. So they pull the chute cord, and my picture of what that looks like is there's the person, and the chute's starting to come out now. It's maybe not fully open, but I'll draw it like that. So what's going to change, drag or weight? Drag. Weight's still the same, but now drag is bigger. And the net force is positive. And if net force is positive and that equals ma, then A is positive. So according to the guy who used to be the head of security here, he used to like to skydive. He said this was the most painful part of skydiving. This is why he had to stop doing it. He had a bad back, and when he would pull his chute, the force was so strong, this net force, that it would yank him upward with a really strong force. So this acceleration is going to be upward, and it was really big. So there was this huge spike right here, and that was the drag of the parachute opening. And then after that, what do you think happened? Your parachute opens. What happens to your speed after that?
Slows down.
Slows down. Does it keep slowing down? No, it's going to slow down really fast to a new terminal velocity of -4 meters per second. I'm just pulling this number out of thin air, but it's going to slow down to something really slow, and then you're going to be at terminal velocity again. And it's going to look like this. It's going to be something like that. So this part, this is number 3. The chute's deploying. Maybe I should have made that a little bit more narrow, because it's just really sudden, narrow, and then comes down like this. It'd be kind of fun to actually do this and collect data, but not me, one of you. And then we get to number 4, which is a new terminal velocity of -4 meters per second. So we had this terminal velocity, and now we've got another one. And I'm going to run out of space if I don't squeeze this in. Here they are. What's always the same? The weight. So it's still the same weight. And if they're at terminal velocity, how big is drag? No. Equal to weight. So if they're at terminal velocity, then the net force has to equal 0. And the drag, it's confusing. I'm asking you because it's a nice trick question. The drag is the same as weight, and what it looks like is they've got the parachute open. So they're falling at a constant velocity with the parachute open. Here's the weird thing, though. Here, the velocity, I'm going to write TV is -40 meters per second. Here, the terminal velocity is -4 meters per second. how is it this person's going negative 40 meters per second and the drag is equal to, let's say, 150 pounds? This person's only going negative 4 meters per second and the drag is the same, 150 pounds, because of the parachute. So at a slow speed, if you've got a really big cross-sectional area and probably a high drag coefficient, then even though your speed is slow, drag can be as much as weight. Going really fast with a smaller cross-sectional area, you can still have same drag. So the drag is the same here and the weight is the same. And this is the same. Okay, so what does that look like? What's the acceleration for this? What should I draw here? 0. So it's 0. And then it's going to stay 0. And what happens to the acceleration when their feet touch the ground? So they're going down, 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 down. And then, so this is number 4. Number 5, I'm running out of space, so I'm going to just, I'll do this. Here their feet are touching down. The parachute is sort of starting to fall like this. They haven't totally come to rest. That's number 5. What sort of acceleration will they experience the moment their feet touch the ground? Positive, negative, or 0? Positive, yes. Because here they're coming downward. Their velocity is downward. They hit the ground, and then they come to a stop. So are they speeding up or slowing down? Slowing down. If you're moving downward, what sort of acceleration slows you down? Positive. So if you have negative velocity, a positive acceleration slows you down. And it's going to look kind of like this, but according to the security guy, it's not going to be quite that big. So there's going to be this big bump, big upward force, and then that's going to trail off, and then you're just going to get to stand there on the ground. So this is number 4, where they're at terminal velocity. Number 2, I should really label like this. It's this whole time when there's no acceleration. This is number 5, when their feet touch the ground. So as always, the person still has weight. So how can it be there's an upward acceleration? What force is stronger than weight that's going to counteract the weight and make an upward acceleration? The normal force. Good job. The other class couldn't think of that word. So there's the normal force. And if you want to put a little bit of drag in, because the parachute's maybe still doing a little bit, you could do that. So you could, I'm just going to do a little D for drag. And the net force here is positive. And then finally, at the very end, they're just standing there, happy to be alive. The chute's on the ground. How many forces are acting on them then? This is number 5. This is number 6. They come to rest. How many forces? 2. There's the weight, and the other one is normal force. And the net force is 0. So there's the acceleration graph. Starts at negative 9.8. That's the only time you're really in free fall. Then terminal velocity. Then an upward force when the parachute opens. Then a new terminal velocity. Upward force when you hit the ground, and then 0. And that's it. That's it for today. The homework, I guess I'll go over that. Homework is page 24 and 26. And there's one kind of problem that doesn't fit, and that's number 3 on page 26. It's like one from the test we already did, but just for the sake of being complete, I'm leaving it in there. The other ones are all about rockets. They're about drag and rocket forces. So page 24 and 26. And the rest of the day, you've got these things to choose from. You can work on your rocket if you want to. We're going to launch next Thursday. I think, did I already tell you the weather's bad on Tuesday? That's what the forecast says. And you can fix up your spreadsheet. I can help you with that if you want. If anybody's interested in trying to splice together bottles, go to the Instructable, go down to the supplies part, watch the video on how to splice them, and once you watch the video, let me know. And I've got hot water, I've got the glue and stuff